Good morning, everybody. Welcome to this fourth day of the workshop. This morning, the first speaker is Daniel Mayerson from Leuven, who will speak about detecting equatorial symmetry breaking. Please.
Thanks. Yes, thank you for, well, thanks to the organizers for letting me talk. And I have to say, I really congratulate them on a good idea, but a good execution of this idea too, because often, you can have a good idea about bringing worlds together and then people just sort of do their own thing and it's hard to talk to each other. But so far, it's been an amazing experience, I have to say, for myself at least, and I think others agree. And so I hope I can contribute at least modestly, right, to this bringing together of worlds. So yes, so I will talk a little bit about something that's become sort of a pet, obsession of mine almost, right? As this idea of equatorial symmetry breaking and why I'm interested in it, but also why it's so why it's important to do this work, this analysis, and essentially because people are overlooking it otherwise, right? So I will talk. So the picture that you can have in your mind is this picture here of an object that is not top bottom symmetric, right? And then we're going to talk about what does it mean if this object is involved in some kind of a thing where there's, let's say, either the object is a fuzzball or a black hole or whatever, and there's something else that's spiraling into it, or there's some photon spiraling into it, right? And so I will talk about, well, there's sort of three papers that I will mainly touch on here, but unfortunately I can only give you the archive number for one of them. So these other two will hopefully be soon. Good. And so let me just tell you sort of what you can expect, right? So I'm going to introduce this idea: what is equatorial symmetry, and how do I parameterize it? So the formalism that I'm going to be working in, and then I will talk about two different scenarios, right, or two different, let's say, arenas where we could see effects of this symmetry breaking. And so the first thing that I will talk about is sort of the context or the arena of gravitational waves, and in particular EMRIs. And the second context will be in imaging, right? So this is maybe going a little bit beyond what we expect at this workshop, which is mainly gravitational waves, but I think nevertheless it's sort of interesting to get an idea of what these things look like also. Okay, good. So let me just let me introduce what is equatorial symmetry, right? This is a symmetry of Kerr, right? So if you write down the Kerr black hole, it has a bunch of symmetries. The symmetries that I think we all study very rigorously when we do the Kerr black hole in kindergarten, right? Is axisymmetry and stationarity, right? So stationarity just means that it looks the same, that it doesn't do anything in time, right? It kind of is relaxed. And axisymmetry means that you have a nice axis around which it rotates, and there's we know that stationarity and axisymmetry are sort of related in a very intimate way in GR. It's not impossible, but it's difficult to sort of relax this link, let's say, between the two, right? But unlike axisymmetry and stationarity, equatorial symmetry is another symmetry of Kerr, which is sort of accidental, right? There's no real deep reason for it to be there. And so just to be really clear, right, this is like sending z to minus c, or reflection, right, or mirroring around the equatorial plane of theta is pi over 2. And so it's saying that the top and the bottom half of the Kerr black hole are the same, right? They are mirror images of each other. And this is a symmetry, but it is sort of accidental. And generically, it's broken, right? If you look at black holes in string theory, generic black holes in string theory, these are not equatorially symmetric. They break it. If you look at any kind of compact object, right, it's a very fine-tuned thing to get this thing to be equatorially symmetric, as you can imagine, right? If you put some structure around the horizon, there's nothing that tells you that the structure on top and on bottom should be the same, right? There's no reason for this. And so this is something that is generically broken in quantum gravity, in things that go beyond Kerr, but it's nevertheless really often overlooked. And so one thing that is often done is, when you think about deviations from Kerr, you say, we assume equatorial symmetry, and then let's parameterize the possible deviations, right? This happens a lot. And so just this fact makes it, for me, interesting to just look at the order 0 questions, like what are the things that I can expect from breaking the symmetry? So I was going to say there is work, of course there is observational work done with dynamical Chern-Simons, and the claim in dynamical Chern-Simons is that there is a multipole that breaks this equatorial symmetry, but as we have understood yesterday, this is actually not true. So even dynamical Chern-Simons does not break equatorial symmetry, so even here there is no link to be made with measuring this effect. Okay. Anyway, so my main question, right, the main question that I really want to ask, and so I would try to ask this in a few contexts, is what happens when I break this symmetry, right? What happens with various observations? Are there fundamental things that I can look at in my gravitational waves, in my imaging, that are smoking guns of this symmetry being broken? Because like I said, if it's broken, we're out of GR, right? We're out of Kerr, and that's what we're looking for. So can we constrain, can we observe this? And so, like I said, this is going to be, these are things that I want to look at, right? I'm going to look at some gravitational wave with MRIs, and then also imaging of asymmetric objects, right? And I think for MRIs, right, so these are extreme mass ratio in spirals. This is a supermassive black hole and a smaller black hole that's sort of orbiting around it many, many times before it plunges into the supermassive black hole. This is interesting because it probes the larger object, right, the geometry of the larger object over many, many, many cycles. And so even if you have a small breaking of, you might expect that these MRIs, right, you accumulate effects over many, many, many cycles. And so this is why this is an ideal arena for finding effects. Okay, so this is why I'm interested, right? It's a generic effect, and people have not really looked at it yet. And so how am I going to parameterize it, right? Concretely, what equatorial symmetry breaking, but how do I quantify this? Well, I'm going to use the multiple expansion, so you may recognize this from Yosef's talk yesterday. Okay, I don't need to talk too much, maybe. And a multiple expansion is like a 1/r expansion. In electrodynamics, this is very familiar to us. We have monopole, dipole, quadrupole, octupole terms, depending on what level of R you're going to. And so as you, well, when you go to GR, like Josef also said, this is a little more subtle because you have coordinate invariance. So what does it really mean to have a 1/r expansion? Nevertheless, there is a formalism where you can do this. And so basically you have the results, right, when the dust clears, is you have two families of multipoles, right? You have mass multipoles and current multipoles, or angular momentum multipoles, which are related to the 1/r expansion, again, of the GTT and GT phi components. I should mention I'm always going to sort of assume and work with axisymmetry, and so then these are really the only numbers that you have, right? You can generalize this to include non-axisymmetric modes as well, right? But so I won't do this for now. And so the Kerr multipoles are these very well-known compact formulas where the even mass multipoles are given by m times some power of a, and the odd current multipoles are given by also m times some power of a. So one thing you should immediately notice is that the odd mass multipoles, right, and the even current multipoles, these are 0 for Kerr, exactly 0. This is an infinite tower, two infinite towers of quantities that are 0 for Kerr. And this is exactly equivalent to saying that the Kerr black hole is equatorially symmetric, right? The symmetry is equivalent to these two towers all being 0. And so you can kind of already see it coming, right? The way to quantify or to parameterize equatorial symmetry breaking is by these multipoles that are 0 for Kerr, right? And so in particular, I will focus on the first, right, the leading order guys that break equatorial symmetry, which is exactly these odd parity guys, S2 and M3, right? So the current quadrupole and the octupole, the mass octupole. Yes, exactly. So M1 is like the center of mass, right? And so because you're in gravity, the center of mass is just. Yes, thank you. You could also, if you are interested, you could think about something called S0. S0 has to be 0 if you're in asymptotically flat space-time. But if you add a nut charge, this is the guy that you turn on, basically, right? And so this is breaking asymptotically flatness mildly. Good. Yes, and please do interrupt for questions if you have any, right? Okay. So this was my introduction. This is my setup. This is my formalism, and now I'm going to go to which is ask, how well can I measure or constrain this guy, right? I'm going to focus on mainly S2 in these emeries with LISA, right, with the Future Space Telescope. Okay, good. So, all right, so that's what I want to do, right? I want to look at an emery, which is a supermassive black hole, and some smaller object orbiting around it. And so to do this, I'm just going to try to be relatively quick about how I study this, right? I'm going to use what's called the analytic kludge or kludge, I have no idea how to pronounce it, for emeries. And this is something that was pioneered by Barak and Cutler. Now, people in the know, they will know that this is a very rough thing to do, right? This is not a very precise way to parameterize your waveform. And so you can't hope to get very precise, very exact results out of this. That's also not what we want, right? We don't want to have exact results about, I expect to find exactly 1.256 or whatever. No, I want an order of magnitude estimate for how well I detect this. Okay. So what's the setup? We're basically going to consider the supermassive black hole as being unmovable, right? It's just fixed at the center, and the smaller black hole is, or whatever it is, smaller compact object is going to is black hole. And we want to parameterize. First of all, the first thing we need to do is we parameterize the orbit of this guy, of this little guy. And so to 0th order, this is of course just a Newtonian orbit. The guy follows a Newtonian orbit. And then we add sort of different effects, right? There's different effects in GR. In particular, it's of course very important that this orbit is going to be shrinking in time. So we add some post-Newtonian effects of dissipation, right? Energy and angular momentum dissipation to some order to some post-Newtonian order. We also add effects from the central spin, right? Because the black hole is spinning. So you add these are all perturbations on the Newtonian orbit, right, in a sense. So we add some leading effects from this central spin. This includes, of course, precession, right? Things like lens steering precession, which is sort of a semi-classical kind of thing. And also dissipation and radiation reaction of this central spin coupling to the orbit of the little object. And then, okay, so then you have some evolution equations, and you could say, and what you're doing, instead of evolving forward in time, we evolve backward in time. We say, okay, look, we're gonna stop the integration when the object plunges into the black hole, because then strong gravity takes over. We can't really do this. We're gonna stop the integration there, and we're gonna really focus on the in-spiral that is exactly 1 year before the 1 year of orbits before it gets to this last plunge, right? So we evolve backwards from this last stable orbit radius. This is, this 1 year is conservative, right? So if you, and this is going to be a recurrent theme, we're conservative estimates of everything that we put in it. And so, right, so because you might expect or hope to have emeries detected that have a lot more than 1 year of data, for example, right? Okay, so that's sort of how we evolve our orbit. And then we need to go from the orbit of the object to a waveform that we can detect in our LISA detector. And so here, it's sort of a very, so again, I'm trying to just give you an idea of this, right? So you have the orbit, and then from the orbit, you can use essentially just Einstein's quadrupole formula to get some emitted waveform, which you then pick up with your detector. You incorporate things that are sort of important for LISA, because we're thinking of LISA, this space-based telescope. So for example, LISA moves, there's some Doppler shift, there's some noise curve for LISA. So we try to emulate as much as possible the conditions that we're looking at. And we normalize the distance by picking an SNR of 30. Okay, normalize the distance to the event. And again, this is something that you might hope is sort of conservative, right? Because, I'm sorry? Signal to noise ratio, sorry. So you can think of this as normal, as picking a distance of your object. right? And so we just pick the distance of whatever object it is, such that the signal to noise ratio is 30. Again, this, it's not so important, right? This is just sort of a choice that you make of the event that you're measuring. And again, I just want to point out that this is sort of conservative, right? You expect to see MREs with much higher, or you hope to see MREs with much higher SNR, which will just give you better results, right? Okay. And so from this waveform, you then have a detection, or a simulated detection, and then you do some Fisher analysis, which means you basically say, given this detection, how well can I extract all of the parameters of my MRE from this measurement, right? And that's and a very rough estimate again of this is given by the Fisher analysis to estimate the accuracy of how well you can measure these things, okay? And so what are we interested in? Things like black hole masses, right? The big and the small mass, the eccentricity of the orbit, the inclination of the orbit, the spin of the central black hole, right? All of these properties are things that you can extract from the waveform and make with some accuracy, right? Okay, so like I said, the analytic kludge or kludge is fast, right? It's a fast doing this. But it's rough, okay? So there are much better ways of generating waveforms, much more accurate, but these are typically not harder, but just more computationally expensive. And all we really want is an order of magnitude, okay? And so Brack and Cutler, they pioneered this, and they used this to sort of estimate that, for MREs, we expect roughly to find, for example, to measure the spin of the central black hole to within 1 part in 10 to the minus 4, right? Which is incredible, right? This is really, really accurate. This is, of course, much better than you can do with ground-based detectors. And the reason is because you have so much data, right? You have so many orbits. And so another thing that Brack and Cutler did was expand this analysis to start to look for beyond Kerr black holes, right? And so one thing that I already mentioned, right, is that the quadrupole moment of Kerr is exactly given by minus the spin squared, right? If you're looking at dimensionless numbers, and this is a prediction from GR, okay? And so the sort of first non-trivial, if you're thinking of multipoles, the first non-trivial guy that GR predicts a specific number for, right? Mass and angular momentum, you just measure it. Once you have mass and angular momentum, the quadrupole for Kerr is completely fixed. Ask yourself, how well can these MREs or the detection of MREs with LISA measure possible deviations from this Kerr quadrupole? And so what they find, right, in this follow-up paper is, this very much quoted number of 10 to the minus 4, right? But it's more like a range between 10 to the minus 2, 10 to the minus 4, depending on what kind of MRE you're measuring, right? But in any case, let's take the optimistic value, right? This is something really precise, right? You will be able to measure deviations from this quadrupole really precisely, which is exciting. Okay. Yes. I'm sorry. Yes. I can repeat the question. Yes, I'm still talking about SNR of 30. Yeah, I believe they always normalize to this.
Yeah, I was just like, it's a bit puzzling to talk because if you have SNR of 30, that means your signal to noise is 30.
Right.
Right? So that means that if you change, but the thing is that if you change things by 10 to the minus 4, it's hard to see how you could, so it's still like 1/100th of your noise. So I cannot quite see the.
I'm not sure. Okay, I'm not sure I understand entirely, but well, he has a microphone.
I just have a microphone. Right?
Yeah.
Yeah, I could be a bit louder. Oh, okay, maybe this is better. Yeah, I'm just saying that SNR of 30 basically means that your signal to noise is 30. So everything you could measure to precision of 1 in 30 within a factor of order 1. Oh, okay.
No, that's
so okay. So
yeah, no.
Gregorio disagrees.
Yes, I can give you the microphone.
I don't think it's that simple. So first there are correlations. Then so the point is how much the waveform is changed when you vary that parameter, right? So there are things to which you're really sensitive because a small variation of it changes significantly the waveform, another not. So take the mass and the spin when you measure from the ring down. The spin has a very small effect because just, the leading order effect is that it makes the ring down longer, while the mass changes drastically. So you have, you measure the spin with the precision of 0.7 plus or minus 0.3. By the mass, you measure it by 5%.
No. So I think maybe a way, at least for the MRIs, I think a way to think about it, right, is yes, you have noise on the signal, but the noise is sort of constant, right? Whereas this effect of let's say a deviated quadrupole, this is something that accumulates, right?
Right, but so does signal to noise. So I mean, if the
Right. Right. Yes, thank you. Yes.
Okay, can you hear me now?
Yes.
right.
And so in this case, the question is how much SNR you lose when you move it a little bit away. I really don't understand how you get to these numbers because presumably there are errors also in other parameters.
Yeah, you have errors in everything. Yes.
So correlation between and how many this corresponds to how many cycles? Yes, that's the point. That it's kind of more number because
So sorry, your confusion is why do you get these really small numbers
I'm saying that
for the measurement?
I'm a little skeptical that you can actually get to that.
That you
No, what I was saying is probably for MRIs, because there are so many cycles,
Yes.
the right question to ask is how many cycles that such a small change introduce?
Yes, so what's the answer?
Right.
I guess the number corresponds to two cycles.
To how many?
Two cycles in a year of.
I mean, if you let's just
So you
throw
said
some
a
numbers,
year,
right?
right? So what is it, 10 to the 4 cycles? So 10 to the 5, okay.
Right.
So
One cycle is here a lot.
yes, and then you have to multiply it by the probability that you see something like that.
Well, okay, this is assuming you see something, right? But yeah, exactly. Like if you, it's exactly this idea that signal to noise gives you, of course, the amplitude, right? This is about the amplitude, whereas the phase will tell you that the guy has done an extra cycle or something like that, right? Yes. Good. Any more on this? So I mean, I think from a purely how should I say this? As a black box, right? This is just calculating for you how much your waveform that you detect will change if you vary a parameter, right? And so the conclusion is there are also parameters that you vary and you don't see them, right? You don't see them very well. There are parameters that are not very well detectable. Luckily, right, for MRIs, these are the parameters that we don't really care about, right? Like for example, how the MRIs is inclinated with respect to the LISA detector, for example, right? And so we don't really care about this so much. Good. So good. So this was sort of a first indication, right? That MRIs will be a really interesting battleground, let's say, to be looking at beyond Kerr deviations. Okay. And so I will use this number when I come back to sort of applications, and so we can see how well, what does this do for us in a concrete example or two concrete examples. But now, for now, let's go on to what I want to do, right, which is basically expanding this again expanding this again to measure equatorial symmetry breaking. And so in this framework, it seems almost very, it is straightforward to do exactly the same thing that Brack and Cutler did, but we just add the effects of these odd parity guys, okay? And so so we take the evolution that they had with including also the mass quadrupole effects. So we don't get rid of those. We correct their equation somewhat, doesn't change the results. And then we add again the precession and dissipation effects, the leading order effects of these multipoles, right? Of these equatorial symmetry breaking multipoles. And so, although I won't go into more details unless there's a need, this is somehow not as straightforward or trivial as you might think, in the sense that M2 when you add the mass quadrupole, it has very much it's not the same, but it has very much the same flavor or same kind of evolution that, for example, the spin has, right? It's very much like a second order spin kind of effect on your orbit. Whereas these guys, when you break equatorial symmetry, right, you have other effects that are very, very different from all these symmetry conserving multipoles. And so, for example, you have effects that you really see as singularities, right, in the orbit evolution that correspond to things like being repulsed from a thing that is, of course, not there for equatorial preserving, right? Because we always like to think about equatorial orbits as being a simple thing in Kerr. Here, there is no such thing as an equatorial orbit, right? So you have to be repulsed from it, and you see this showing up. And so, yeah, okay. So I won't go into more detail of this, but this is why this is an interesting phenomena, because you expect to see things that are so different than the symmetry preserving effects, basically. Okay, so I will focus then, so we focused mainly on this symmetry breaking parameter, right, this tilde M1, which you can think of as sort of a dimensionless number that tells you the strength that quantifies for you how much the symmetry is broken, okay? And so then you ask yourself just a very simple question: how well can we detect, how well can we constrain this, this parameter, right? So it should be 0 for Kerr, okay? So how much off 0 can we measure it? Is there a question?
Why do you assume that S2 over M cube is equal to M3 over...
Yeah, good. So this is just, okay, so we did it like this, right, where we say these guys, the dimensionless variant is the same. We also just considered S2 and left M3 for what it is. We did various mixes. Now I'm just focusing on this, right? You get the same. Yeah, you get the same, basically, yes. But yeah, thanks. Good. So we're measuring this the symmetry breaking parameter, and so a representative measurement, right, which is this guy here. So for example, we have the central object has 10 to the 6 solar masses. The small object is 1 solar mass. The spin of the central black hole is sort of is not too much, not too little, and we have a little bit of eccentricity, right? So it's a low eccentricity orbit. So okay, so this is sort of the parameters that we are looking at for this particular emery, right? We're looking at one event, and then this is all measurement accuracies of the different parameters, right? I will not really go over many of them. The main thing to see is that these are all small numbers, so we're able to detect things very precisely, like I said. For example, we are able to detect the deviation from the Kerr quadrupole, right? 10 to the minus 2, 10 to the minus 4, like I said. Brack and Cutler showed, and so again, we find something that is within this range. And so for us, right, this new parameter that we're detecting is this change, or this symmetry breaking parameter, right? And so the number that I would like you to remember, right, is this 10 to the minus 2, or I like to say 1%, which is the accuracy that we expect to see this effect, okay? And so this I say this is representative. Of course, we looked at all kinds of different emeries to be sure of this. And so I will just very quickly show you a few of these analysis that you can do, right? So for example, so what I always do is I plot the accuracy that we're talking about on the y-axis, and on the x-axis I vary one of the emery parameters, right? So for example, here you see that the measurement accuracy is basically independent of the central spin of the black hole. The eccentricity is sort of the only right? So this middle graph, the eccentricity is more or less the only parameter that affects it a little significantly. And so you see that for low eccentricities, you actually get a much better accuracy of this parameter. This has to do, again, with these special sort of evolution, the special orbits that you get from breaking equatorial symmetry. At high eccentricities, it gets a little worse, but we can't really trust this model for high eccentricities typically. And so also for lambda, the orbit inclination, right, how the orbit is inclined with respect to the spin of the central black hole, there is basically no change. You should note that this is not a logarithmic scale anymore. And the peaks that you see at 0, pi over 2, and pi are basically coordinate singularities. So it's harder to trust your results there. But even there, it's not so much different. Okay, so this is just to show you that, you know, this idea, this 10 to minus 2, this 1%, this is sort of robust, right? This is the order of magnitude, which is all I really wanted to extract from this analysis. This is the order of magnitude that you should expect to see this effect at LISA. Yeah?
And yeah, one comment related, one question related to this.
Yeah. I'm sorry, the second. Ah, good, yes. So you're asking about effects of the secondary spin. The second, yes. Yes, no, that's a very interesting question, I think, yeah. No, I don't know, no. So in this model, we don't have these effects. I don't really have any intuition either way. But I would expect that you should still be able to distinguish them because they give you sort of different. They still do right, and that's the point also about these symmetry breaking things is they give you really different effects on your orbit than most of the other kind of precession or whatever do. But again, I don't know because I haven't.
Actually, maybe a related question to understand this is. Are there differences in the errors on either this M1 or M2?
Ah, good. Yes. So what you can do, right? You can also play. This is the nice thing about the analytic kludge, is you can. It's very modular, right? You can play around with what effects you do and do not include. So I was kind of expecting some remark also maybe about the fact that these guys enter in a PN order that is actually higher than the dissipation that I'm taking into account, right? And so you might be worried about, well, there's also PN effects, there's also dissipation effects at these orders. And so what you can do to show yourself that your results are robust, even though they're sort of not consistent at a consistent, is you can leave out certain terms. You can show, for example, right? These are two orders of dissipation effects. You can take both of them, or you can take only one of them, and you can see that the effect is negligible, right? These kind of things. And so you can also take out spin effects. You can take out, you can do all of this, and you see that it's basically the same always. Yeah. Thanks. Okay, so I think good. So now I will go on to an application of where you can use these numbers, right? Any other questions on this first? No. Okay, good. So I will do two applications, right? So I will talk about two applications where you can use these numbers to constrain models. So one is going to be sort of this was already touched on by other people in other talks, right? So this is going to be completely analogous. We can talk about sort of two different kinds of deviations, let's say. And one is where the scale is set by a solution that I will talk about is the almost BPS black holes. And then you can also set, I say scale set externally, you can say that this is basically like the scale is set by the theory, let's say, right? So there is a Lagrangian with a parameter in it that sets a scale for you. And the example here is going to be higher derivative corrections. And so you'll see that, the first one is going to be interesting or optimistic, and the second one is less. So, so if the scale is set by a solution, then, we're going to use, I should say what we're doing. We're going to use the constraints for the mass quadrupole and that Barak and Cutler found and the current quadrupole that we found to constrain these models, right? To give you an order of magnitude estimate again of how well we can constrain these models. And so, for example, we're going to use these almost BPS black holes that Josef and Ibu and Pierre, I don't know why it's doing this, and Yishuan and we did last year. And right, we were trying. What we're doing, our philosophy was not to find the black hole that we are finding in the sky. Our philosophy was to find more and more realistic black holes and models and microstates in string theory that we could use to look at observations, right? And so these guys are interesting because they're not supersymmetric, although they are still extremal. And you also have this tunable parameter h, which in a certain limit you can make it so that the black hole has very little charge compared to its mass, right? And that's an interesting thing, of course. Okay, but in particular, right, not giving you the details of these black holes, if you look at their multipoles, and in particular these two multipoles that I'm talking about, you see that this parameter h appears in their multipoles. And so what you can do is you can say, look, the bound on M2 is like 10 to the minus 4, right, optimistically. And so let's just match the Kerr quadrupole, okay? So our model has this parameter h, which we can set to 1 over square root 2. And then the Kerr quadrupole is given by the quadrupole is given by minus the spin squared. Okay, so we can match the Kerr geometry up to the mass quadrupole. But then you see that S2 is going to be, well, it's not going to be 0. And so this is measurable, right? Kerr, it should be 0. And so for this guy, it's not 0. And in particular, right, if we take this 10 to the minus 2 seriously, then this means that we could rule out this model, right? We could detect this kind of black hole if this was at the center of an emery, if the spin was very modest, right? Or the spin has to be only very modest, right? 0.1. So anything that's spinning higher than this, we could definitely see in this S2 effect. Okay, so that's pretty good, right? Because this is just a very modest spin of the central black hole, and so this would be a pretty good constraint on the model, right? So this is one example where this kind of constraints really gives you something nice on your model. Okay, so that's the scale set by the solution. If you want to do a scale set by the theory, let's say, which means basically it's an input in your Lagrangian, right? In this case, we're looking at higher derivatives. In higher derivative corrections, you have to introduce a new length scale in the Lagrangian. So here, I give you sort of the schematic form. You have some, okay, I don't include 4 derivative corrections, but you can. But if you look at 6 derivative and 8 derivative corrections to your GR to your gravity Lagrangian, then you see that this, of course, introduces a new length scale in the problem, right? Good. And so this scale, where does it come from? Well, if you expect that it's set by quantum gravity, it should be really small, right? Planck length order. But obviously, we will not be able to see anything near this. Okay, and so there's two. Okay, so if we take these higher derivative effects seriously, there's 2 different effects. There's an effect where emeries, right? Thinking about emeries. There's the effect where the central object has a perturbation to its metric, right? Because the higher derivative corrections change the metric. This is like a finite size effect, right? This means that when your metric changes, your multipoles change, and so you can calculate this. This is what we're working on now. You can calculate the change in all of the multipole moments and see that there are some order 1 number times this the only length scale that you could really make. And then there's a second effect, right? So this effect is like a finite size effect where the metric changes, and so the geodesic, let's say that the guy is following changes. Okay. Then there's the effect where the radiation, of course, couples to the orbit of this binary system in a different way. But you can show that again, the Einstein quadrupole formula is the leading order effect on the radiation, and the higher derivatives gives you sort of a renormalization of what the quadrupole is that couples to the radiation. Okay, so this was done by these guys, at least for the 6 derivatives. And so you see that you get some nice, some interesting renormalization, but it's very simple. So it's very simple to take into account. And in particular, right, when you're thinking about emeries and the in-spiral phase, these things are subleading, okay? And so the finite size effects from these multipoles are the things that are the leading effects that they expect to see. And so, good. So the leading effect, right, these multipoles. And so, okay, we just immediately translate our results to a constraint on this length scale, right, which is the only sort of interesting parameter, interesting scale in the solution. And so there you see that, you know, even just focusing on the quadrupole, this is dimensional analysis essentially, right? But you see this, that it's not so effective to constrain these kind of theories, because you get a suppression by the supermassive black hole mass, right? This is essentially the same thing as saying the supermassive black hole, because it's so big, the horizon scale is at the horizon scale, you don't have a lot of curvature. And so unfortunately, this means that, you know, you're not going to be able to constrain this scale very much. You get a constraint that is something like this. And so in this case, right, Lisa emeries are not the thing to look for, even though you can constrain things very well. Ground-based detectors with ET, you know, you can estimate that it's going to be like tens of meters more than thousands of kilometers. So that's just sort of a, for me, this was, you know, I know this is obvious probably for observational people, right? But for me, this was interesting to see. You really need to distinguish these two kinds of models, right? And one of them you can constrain very well depending on your model, the other one perhaps not. Okay, so I should pause here for any questions.
One question, in both cases, both applications that you were mentioning, don't you expect also, say, dipolar radiation or any way other dissipative effects that might actually be?
Yeah, so, okay, so I'm taking out, you know, for you mean like the CPS, it has charge, you expect a dipolar emission. Well, but the radiation, I think, is going to be subleading in this case, right? The effect of the higher derivatives on the radiation will, you know, because of this suppression here, you don't see it, you don't see it so much. Yes, for the in spiral, right? And then, okay, in the merger, it's, yeah. But yes, for the almost BPS for sure, I'm sort of cherry picking my effect, right? There will be other effects coming from dipolar emission and et cetera. Yeah. Agree. Any other questions here? Yeah, there's a question back there.
Thank you. So I guess maybe this is what you already answered, but I'm just thinking that there will be tidal deformation of the object by the orbiting, I guess, a smaller mass object. So is that something that's important, or yeah?
Yeah. So for higher derivatives, okay. So we haven't done it in this fully general story, but for I want to say the sixth derivative case, there are some numbers, and they don't give you. They essentially give you the same order of magnitude of constraints as the multipole constraints will. If you plug them into how well we can constrain the love numbers and translate that to the length scale, you get the same numbers basically. If that was your question.
That's an additional effect to the effects that you're considering, isn't that right?
Yeah,
okay.
It's a different effect. Yes, absolutely. Yeah.
Thanks.
Okay, so then I'm gonna change, let's say, arenas, but still focus on the same phenomenon, which is the breaking of this equatorial symmetry. And I'm gonna go to, basically the question will be, okay, I have some object in the sky, I want to take some picture of it, right, EHT, et cetera. How will I be able to see equatorial asymmetry? Okay. You don't really take a picture, yes. No, I'm not gonna go out there with my camera, no. That's right. Okay, so the question is, right, can we see the breaking of equatorial symmetry in these images? Okay, so what is gonna be my setup? Because I'm gonna use these 4-color screens a lot, and if you haven't seen them before, it might be confusing. I'm going to imagine that I have, my black hole that I'm looking at is at the center of the sphere here. And I put the camera on one of these edges, right, this white edge that you see there. And then I imagine that there's this sphere at a very large distance that is divided up into 4 quadrants and that emits light in these 4 different colors uniformly, right? And so what then happens is, you know, my camera will pick up the light that comes from this sphere, If it was, flat space, I would just see, 4 little squares, right, of the different colors. But since there's an object that deforms the trajectory of these photons, I see, of course, something deformed. And so in particular, I'll see a big black shadow, as it's called, a big black hole in the center because some statistics here. And for the rest, I'll see, when I'm very far, when the geodesics don't really travel close, they will just look like they came from wherever they came from. But then when you get closer and closer to the black hole, you'll see that there's more and more lensing effects and bending effects, and these tell you something about the geometry, right? That's the idea. So I just want to be really clear on terminology, maybe, because I think that's important. The image is the light that you see. The shadow is this absence of light in the middle, okay? So just to be clear there. Okay. And so, okay, these are 2 pictures of a Kerr black hole where here you have your inclination is 90 degrees, which means the black hole is orbiting around the y-axis here. And here the inclination is 60 degrees, so you imagine that you're sort of tilted, the axis of rotation is sort of tilted towards you. And you see that if you see, the first thing that you see is that we're interested in equatorial asymmetry, right? You see that if you have an inclination, you sort of automatically have some kind of asymmetry in the image, which is obvious, right? This has to be there. But of course, at 90 degrees, you don't have this asymmetry. Okay, so the first thing to point out is, I think, a very curious thing, which is that you can easily break the image asymmetry. Okay. So like I said, if you just took that curve, for example, at a different inclination, then you break the up-down symmetry, of course, just naturally by looking at a weird angle, and then you have an image asymmetry. You can also look at black holes which break equatorial symmetry. And so this is an example of a Rashid-Larsen black hole. Doesn't matter what it is, but it's a black hole that breaks equatorial symmetry. And so you see, right, this is at 90 degrees, but nevertheless, you see asymmetry, right? There's these features that are not up-down symmetric. So it's very easy to you have an asymmetric image, but something that is sort of very curious, and intuitively I can't give you a nice explanation. Mathematically, it's obvious. The shadow will always be symmetric. Okay, they'll always be top-down symmetric, always equatorial symmetric. Okay, this is true both for Kerr at some weird angle or whatever, and it's true for black holes that break the symmetry themselves, right? So here, although it's a small image, it's not the best picture that I have, but if you really study this shadow, you will see that it is symmetric, right? It is up-down symmetric. Okay, and you can see this very easily from the equations that define the shadow. From that, this follows immediately from integrability of the geometry. What do I mean by integrability? If your null geodesics are separable, if they're integrable, then you will have a symmetric shadow. Okay, and this was pointed out here, although it may have been sort of known before that already. But it's very easy to see this from the math. So this is sort of very curious, right? Because the first thing you would say is, well, if you have asymmetry, you just look at the shadow, right, which is sort of this order 0, this very distinctive feature, and you see asymmetry there, but you cannot. Okay, so but I also kind of told you what to do, right? So you need to break integrability, and so you need to break equatorial symmetry and integrability to find a shadow that is not symmetric, and so. Some of you know I've been asking around, like, do you have a black hole for me which satisfies certain criteria? And 2 of the criteria are that they break equatorial symmetry and break integrability. I have not heard of any examples yet. But for example, you can use something called the Manko-Novikov metric, which is basically you take a black hole, Schwarzschild in this case, and you give it a little bump, right? So in this case, we give it a little M3 bump. This is still a solution for a vacuum Einstein equation, and therefore it cannot be regular. So there's a mild singularity on the equator, which we're not happy about, but you can sort of see that it doesn't really affect the image too much. And so this breaks equatorial symmetry and geodesic integrability, and you see the shadow looks not symmetric anymore, okay? So this is, I mean, there you go, right? This is something that you could say, wow, I look at the shadow, right? If I have my EHT image, I see, is it top-down symmetric or not? If it's asymmetric, boom, no Kerr, no GR, right? You break GR. So, right, so this is the asymmetric image and the asymmetric shadow. Okay, and I just want to point out, you see that there's something weird going on inside the shadow. This seems to be a general feature of integrability, of breaking integrability, where you have holes in the shadow, right? And so this is related to chaos. And this is not related to the singularity that you have in the metric. It's related really to the fact that you break integrability. Okay, but that's not really the focus I have here.
Sorry, Daniel.
Yes.
So one question. In EHT, in fact, you don't really see the shadow.
Yes. Yes. Right. Okay. Let me go on. Yeah. Okay. So yeah, this okay, good. So this was all very nice and theoretical, right? But like Paolo is getting to, the question really to ask is this observable, right? Okay. And so there are two things to say about the shadow, right? The first thing is usually so observationalists are not really interested in the shadow so much because first of all, there's a lot of degeneracy of the shadow, right? A lot of perturbations of Kerr will produce a shadow that looks exactly like Kerr. So the only thing I want to point out there is that this asymmetry is very much not, this breaks the degeneracy with Kerr shadows, right? Any asymmetry of the shadow is not like this is a smoking gun, right, of not GR. However, the shadow is not a direct observable, right? As Paolo was hinting at, the shadow is not a direct observable. What we observe, of course, is the light that comes from our plasma, right? So the next question to ask is, okay, I understand a little bit about the theory. What about if I now really think about the observed images? What can I see there? Okay. And so like I said, the shadow is not really an observable. We really need to focus on the light, okay? And so there, you might think, well, the asymmetry in the image will give you something, right? Because like I said, you have equatorial symmetry breaking. You break you have some image that breaks this that breaks the symmetry as well. But the plasma, right? The plasma that is generating the photons for you is a very well, it's a very ill understood thing, right? We don't really understand a lot of the details of the plasma that emits the photons, but we do understand that it can be very turbulent, it can be very asymmetric, without the metric being, right, even in Kerr. And so the plasma asymmetry, or the uncertainties in the plasma, it certainly seems like, at least for any sort of naive, just looking at the image observations, this is not going to help you, right? Because the plasma asymmetry is just going to dominate, okay? And so for things that are directly affected by this, things like the direct image and also the jet power that you get from this kind of setup, you just don't see this asymmetry, right, in general. Okay, so this is to be continued. This image, by the way, is an equatorial asymmetric object. It's a Rashid Larson black hole image with some GRMHD plasma around it, right? Which is done by this PhD student Lorenzo Kukler at Leuven in Brussels, who is great with this stuff. Okay, so so then we ask ourselves, okay, is there something that I can observe? And the real observable here is I think the only real observable that is going to give you detailed information about the geometry is the photon rings. Okay, and here on this simulated picture, you can really see the photon rings is like this bright circle, right? This bright circle here. And the way to think of the photon rings is that light, if it travels really close to the innermost orbit for photons, right, what it will do is it will travel around the black hole many, many times before it exits. And so there is an infinite series of photon rings, right, the nth photon rings, etc. The nth photon ring is created by photons that travel around the black hole n half orbits, okay? That's sort of just definition. And so what you can see theoretically is that, as you get closer and closer to the shadow, as you approach the shadow, you go to higher and higher n in your photon ring, right? The photons travel around higher and higher, more and more times before they escape. And these really encode a lot of information on the geometry, okay? If you zoom in, this is again a 4-color screen. If you zoom into photon rings, right? So here you have the shadow, and then here you start seeing the different rings. So in particular, right, n equals to 0, so it hasn't traveled around at all, is the direct image, which is way over here. N equals to 1, so this is travel around 1/2 orbit before coming out. N equals to 2, so travel around the full orbit, et cetera, et cetera. Right, this is something that you can see when you really zoom into this near the shadow region. And so, okay, so this looking at this picture, this picture encodes a lot of information about the geometry. Okay, in particular, the widths of these photon rings are something very important, because the widths of these photon rings are related to the Lyapunov exponent. Okay, each successive ring has a width exponentially suppressed by e to the minus gamma, where gamma is the Lyapunov exponent. This is geometric data, right? So if you can measure the widths of these rings very precisely, then you will be able to extract very precise information of the geometry. And it's important to mention that this is sort of, you bypass the uncertainties of the plasma, because you're looking at a very, very small region of space where photons are emitted from. Okay, and so you don't really care about the details of the plasma. Good, and there's also this idea that also the shape, in particular of the n equals to 2 ring, might carry information about the black hole geometry. But this is all sort of, let's say, work in progress, right? Because I think, except for perhaps a paper that came out today that I haven't read yet, nobody has really looked at how the properties change of these photon rings as you move away from Kerr, right? It's clear that it encodes geometric data, but how much do you have to deviate from Kerr to see measurable deviations in these photon rings is still an open question. People have not studied this. And in particular, right, just to make a comment about observability, with EHT currently, you don't expect to see all of these photon rings. We don't have the resolution for this. There's ideas for some space-based imaging that might be able to let you see the n equals to 2 ring, and so that would be enough to look at like the n equals to 2 shape. But so to really measure like successive widths of these rings, you would need to go even higher, and so this is sort of not in the cards for the near future, I would say. Okay, so I'll finish up. Any comments here or questions on the imaging? Yeah. Wait.
I mean, there might be a correlation. I mean, there is a correlation between this width and the quasi-normal modes, because it's so
it's
that
a photon
would be
ring,
also
right? So
a cross-check of the model.
a cross-check of the. What do you mean by a cross-check of? Good. Right. So you can make like a So the quasi-normal modes will be affected, and also your photon rings will be affected, and you can make Yeah. Exactly. Yeah. Absolutely. Okay. Any other comments?
Maybe just a follow-up comment on this. I think that Wang Yang, Nayesh, has a paper on essentially the correspondence between shadows and quasi-normal modes, right?
Huh. Okay, so this was sort of all I wanted to say about the images. Since I'm basically out of time, I had 2 slides where I would go beyond what I'm talking about here, but I will just leave this. I think for me the. We have still 5 minutes. Okay, no, for me it's fine. Yeah, okay. Okay, good. So when I prepare my talks, I practice, and then I notice that I am well ahead. So it's a good activity. Yeah, of course you have to do this. And so I've said, perfect. I can talk about, I can speculate and start discussion, right? So good. Here's a quote from Hughes. So this talk, right? What I was talking about was equatorial symmetry and breaking it, right? And this has been sort of this pet thing of mine, asking where you can see this. And where did this come from? Well, basically, we had this project where we were imaging Rashid Larson, right? And I saw, oh, this is not symmetric. What's going on, right? Must be your code is wrong. And then I realized, no, of course, the metric is asymmetric. So you see this, and then I realized, looking through the literature, that this has just not been looked at. Okay, and I think this, for me, this is an example of a feature that is prevalent in this case, string theory, because I come from, string theory fuzzballs, that is very, very obviously present, but that sort of hasn't or wasn't really explored enough, at least to my taste, in phenomenology. And so I said, okay, let's take a look. And so I think, this is a general thing that I would like to do, is to take, signatures that you see from quantum gravity, from string theory, from fuzzballs, and try to rework it or try to isolate, whatever universal feature you can, and to use this as some phenomenological input, right? That you may not think of otherwise if you just start from GR and you ask yourself what could happen. And so I just had two, let's say, ideas, right, that I'd like to share with you. And the first one is, at the merger, of course, we all know, excuse me. We all know that the merger is where the strongest gravity is, and so therefore strongest gravity means strongest corrections to GR that you might expect. But there's also, very concrete things in string theory where we see this shouting at us, right? That this is where there may be really big, strange quantum effects going on in this merger phase. And so there's three different avenues, right? Completely orthogonal avenues where you see this. I won't go into a lot of details, but please ask me more if you want to know more. There's this idea of non-local effects that are present in black hole geometries, where at least Papadopoulos Majou, I like to say this as the most concrete calculation that you can do. There's also islands, but I understand less where this is coming from. But the idea here is that there are non-local effects where they're small, that you don't really see them as a semi-classical observer, right? If you have a really big black hole and you're some observer that can do semi-classical observations around it, they're exponentially suppressed. You don't see it. But where does this exponential suppression break down? It's exactly when you have a large perturbation at the horizon. So in particular, if you're thinking about a merger scenario, when you bring the two black holes close to each other, you cannot say that it's a small effect anymore, these non-local effects. And so in particular, I would expect that at some point when you bring the black holes closer to each other, these things might start dominating. They might give you a big contribution, right? So these are quantum effects, quantum non-local effects that become large when you bring the two black holes close to each other, right? So I just to be specific, what I'm talking about here is, right, you expect from general grounds that quantum effects are the largest at the merger. Here are some very concrete scenarios where we see this happen, right? That's sort of the thing that I'm trying to give you. The second was something that also Joseph talked about yesterday. We understand that fuzzballs, right, when you collapse a shell of matter or when you merge two black holes, what happens when you get to the horizon scale is you have these quantum tunneling effects near the horizon. So again, this is something where these quantum effects become large, become important when you're at these horizon scales, when you bring the black holes really close to each other. And then this third hint is something that I think is a really interesting thing that not many people are aware of, I think, is in this scattering formalism, right? There was this paper called Silence of Binary Kerr, right? Where what they do is they look at these particles that Rodolfo was talking about yesterday. They look at scattering of particles, right? And they see that and they look at the entanglement entropy that's generated in such a scattering. And then they see that when you look at the particles, so these coefficients, right? When you set these coefficients of the particles to be exactly those of Kerr, that's a minimum of the entanglement entropy generated. So the way I interpreted this is to say that, Kerr black holes are this very special extreme point of this in the scattering amplitude business, extreme point of this let's say quantum effects that go on, right? Entanglement entropy being a measure of this, And when you move away from this, when you look at deviations of Kerr, when you look at fuzzballs or whatever what you want to look at, you will find something that generates, scattering of these guys will generate more entanglement entropy. So this is, again, something where you see, this is, again, a quantum effect that is big for for non-GR geometries. So the big question is, how do we see this, right? How do we model this? Because this is about the merger phase. But hopefully some kind of intuition or hints of how to model this from these concrete string theory calculations, right? And the second thing that I wanted to point out, again, I think Joseph talked about this, right, is these stringy tidal forces, where when you have a fuzzball in particular, you throw something in, of course you expect to see tidal forces, right? Because a black hole has tidal forces as well. But there are these extra tidal forces which are in the black hole, they're absent in the black hole. And these extra tidal forces, not only are they not there in the black hole, but they happen way before you would expect, right? What you would expect is that you only experience a difference, right? You only have a different experience when you start exploring the fuzzball itself, right? When you start exploring the microstructure that is sort of at the horizon. So you really need to get really, really close to the horizon is what I'm trying to say to see them. But these stringy tidal forces, they appear before you get to the structure, okay? So this means that particles may experience these stringy tidal, may feel them way before you get to the actual horizon scale, okay? And so in particular, what might happen, or one thing that does happen, is that massless particles, right? Massless particles, you can think of them as a massless excitation of a string. They will become massive because you excite the massive excitations of this string because of these stringy tidal forces. And so this is something you can model, right? You could say, what happens if I have, let's say, photons that have a position-dependent mass, or even in MREs where your black hole mass depends on where it is, or something like this, right? So these are just two effects that I just wanted to start discussion, because after all, this is a workshop, right? I think these are really promising, interesting effects that come from string theory, come from fuzzballs, or from other directions in string theory that can really help us model some kind of new effect that might be observable. All right, so let me wrap up then. Let me wrap up. So what I was talking about here, except for the last two dream slides, let's say, is this breaking of equatorial symmetry, which I hope I've convinced you of at least the fact that it is, if you can measure it, it's a smoking gun of not having GR, right? And so how observable is it is a question that you should be asking. And we gave some first indications that maybe it's surprisingly well observable, right? And so using MREs, you can sort of see that you can observe this to within 1%, right? I like this, which translates either into a good or a bad model constraint depending on your model, like I saw. And so also in imaging, you can see this in the shadow if you break integrability as well, but it's still sort of an open problem if you can, how well you can distinguish this in actual image observations, right? So this is, but it can still be exciting in the future. Okay, thanks.
Okay, thank you for the very clear talk, also for the non-experts. Are there more questions? The microphone over, please.
Yeah, now.
Oh, okay. So I think.
No, I think. Maybe the other one.
So when integrability break, shadow become asymmetry. Can you observe the Lyapunov exponent?
Okay, yeah. So the Lyapunov exponent, I think the most obvious place to observe this in images is in how the ring thicknesses change. Right?
No, it's Lyapunov exponent of light ring, right?
Yes.
My question is Lyapunov exponent of the coming from non-integrability of spacetime. It's different, no?
Okay. I wouldn't know exactly how to translate this into an observable, I guess. But perhaps, yeah. This is, we haven't thought about this long, so I would be happy if you have, where does this appear, right? This particular breaking of integrability and the associated exponents. Where could I see this? I don't really. So.
Other questions?
Yeah, regarding effects which are typically neglected GR, but might actually be generic smoking guns. How about breaking of axisymmetry and therefore maybe having multiple tensors or?
Right. Yeah. So yeah. So good. So you have a nice paper, right, about measuring this kind of effect, but also for axisymmetry breaking. And so I think also this is I did not focus on this. I think that's also something that you will see. From my point of view, just because I see in for string theory black holes, for example, I see that or black holes in general, it's very easy to break equatorial symmetry, but it's harder to break axisymmetry, right? Because it's sort of there are these theorems in GR where it's hard to get around breaking axisymmetry if you want stationarity, right? But not impossible.
Do they apply also in a modified gravity, those theorems?
Right, no. So I know there are counterexamples, right? So where you do have examples that are not axisymmetric. And also compact objects are not generally axisymmetric either, right? So for sure. But I think for me, this will also give other effects, I guess, right? So because if it's not axisymmetric, but it's spinning, you expect that this gives you already a continuous signal that is an extra effect that might be leading, I guess. I don't really know. Might depend on, yeah. But no, this is definitely interesting, right? Yes. No. Breaking symmetries in general that you have in Kerr, this is right. This is the way to go. Yeah. Absolutely.
Yeah. Daniel. That's the question I had actually. So this is the question I had. If you break axisymmetry, don't you get radiation? I mean, the object in principle just radiates like crazy until it loses whatever energy it has and whatever spin it has. So if you have some object and you break, let's say you put a mountain on a black hole. You could imagine some structure, and you have it rotate. You're just going to emit Hawking radiation because it will not be stationary anymore, and then it will just emit, sorry, not Hawking radiation, just normal gravity radiation. Yeah. And it will just cool down, and over time it will just stop.
Right. That's what I was saying. You have this continuous emission that you have, but yeah.
Yeah, you would admit that the question is then the time scales. I mean, this, for example, has been studied for neutron stars, and in fact, I mean, like in Virgo are looking for signals coming from essentially mountains on neutron stars. Yes. But those are continuous signals precisely because on the time scale of the observations, essentially they are not changing the spin in an appreciable way. I see. But so for an inspiral, you would expect that, I mean, during the whole inspiral it would be...
But the life of neutron stars is much shorter in a sense. So, they can get the mountains and then, the mountains are there and then at some point, I mean...
No, why shorter? I mean...
When you have a black hole, like a super mega big galaxy mass black hole, which MRIs are going to measure, that happens around for gazillions of years. So, essentially that, I mean, whatever bumps that
right.
time ago.
I think it depends on how big it is, right?
Yeah.
I mean, eventually any black hole comes from a neutron star, most likely. So
sure, but the one in the center of the galaxy. So if you have an MRI, you expect like a galaxy mass black hole with a tiny blip around, and the galaxy mass black hole, which is the one you want to measure the mountains on, has been around for like 5 billion years or something. So in that time we probably shed away all the angular momentum it has. And so probably can rule out mountains on this black hole even by looking at our current observations, because I think the black hole in the middle of the Milky Way has rotation. I don't know. Do people know if the Milky Way black hole in the middle has rotation or not?
It'll emit rotation. I mean, it'll emit.
Does it rotate, or is it scorched, or is it curved? The black hole in the middle of the Milky Way.
The measurements are very bad, essentially. Yeah. You don't really know. It should be spinning, but you don't know.
Because if that one is spinning, then you can probably rule out mountains. At least you can rule out some sort of mountains, because if it's spinning, it has been spinning around for like 10 billion years. So then
Yeah, you can compare the time scale. Yeah, I guess you can compare the time scale with the dissipation. Yeah.
So, sorry to chime in, but on this argument, but if you look, for example, at supermassive mergers in LISA, and there is a solution which might sustain non-axisymmetry, then you might just form a non-axisymmetric black holes just by mergers. Yes, exactly. And LISA will observe that immediately right after it merges. So you could see this immediately in not in MRIs but in supermassive black holes. Yeah. I think that.
Yeah.
Well, it's in line with what is being discussed. So even in GR, you can have non-axisymmetric black. You can have not stationary. Let me call it equilibrium solutions.
Yes.
That are not time independent, that are not axisymmetric. Nevertheless, they have a killing vector field that is a linear combination of the dt and d phi. That is also the horizon generator.
Right.
So it vanishes at the norm of it vanishes at the horizon. And if you want, this is a kind of, so there are solutions, these kind of solutions for m equals to 2, 3, 4, and so on. So m equals to 2 would be a kind of a peanut that is rotating, so that the period after which it comes back, like a lighthouse, is always the same. So there is some equilibrium, some periodicity in this sense.
Right.
But it's not axisymmetric. And this can exist even in pure gravity if we are in ADS.
Right, but so there, I mean,
the net result, it emits, it's a periodic solution, so it's an equilibrium solution. So if you want, it emits, but it absorbs at the same rate.
but only because you're in ADS, right? I mean, this is why.
No, but then you can go to the asymptotical flat case, and if you have a scalar field, it's not just pure gravity, but you can have a cloud of scalar field that is doing the same job.
Right.
That also has this peanut shape, rotating peanut shape configuration. We call it, so in ADS, it was a paper. The original paper is from 2011, and it's Gero Horowitz, George Santos, and me that found it with a scalar field. In that case, we were using a special scalar field. It's a doublet, so that you break axisymmetry on the scalar field, but because then the scalar field is a kind of a complex scalar field in the energy momentum tensor, it cancels, so the metric itself is axisymmetric. But then you can go to pure gravity, and we found it in pure gravity in ADS, and it was George Santos, Benson Wei, and me, 2015. And then in GR, you have the Erdero-Radu solution, which is basically a Kerr black hole with this air going around. So the mass of the scalar field provides you the potential to trap the scalar from X. It emits, but it absorbs also. You know, in ADS, you can understand this very well. In asymptotically flat, I think that that I don't know is.
May I suggest
it's because of the scalar, right? The
scalar
scalar provides the ADS reflection or whatever.
I think that the field itself should still preserve axisymmetry, but the whole solution also includes the scalar field, and the scalar field itself gets trapped at this potential well.
Right.
It's massive, and it comes back. Of course, this works only if the gravitational field itself is still axisymmetric, which I think it is, because I think it's along the same way of our original solution in ADS with the scalar field, and in that case, that's definitely the case.
Okay, I think we should go on with the discussion this afternoon. Otherwise, you should keep coffee. So let's thank Daniel again.